Hello, Eugene Aiello here. Thank you for watching the next video in my series on patient education. This video is going to be a fun video. Again, it's probably going to be one of those that after you're done watching it, you're going to know more than your doctor does about health. Oxidative stress is a huge topic in science right now. Most disease processes are the result of oxidative stress. They've shown that cancer, the root cause of it is oxidative stress. All degenerative disorders, I'm talking neurodegenerative, I'm talking arthritic, I'm talking anything that's degenerating of the body with age. Inflammation leading to pain, inflammation leading to heart disease. Heart disease is a disease not of imbalanced cholesterol levels or lipids. Heart disease has been shown that it's inflammation of those inner linings of the arteries leading to calcification and atherosclerosis. The fat is the secondary aspect of heart disease. Once you have atherosclerosis, calcification of those arteries, fat's going to stick to it. So when they go in and see a fatty plugged artery, it's not the fat plugging it, it's the inflammation of the arteries. Aging, wrinkles, gray hair, vision. I could probably go on and on. Basically, anything that's going to happen where our body is going to break down over time is the result of oxidative stress. The causes of oxidative stress are actually normal, meaning stress. When I say stress, I'm talking mental stress, I'm talking physical stress. When we're demanding more of our body and our body's working harder, and as we're going to talk about in a little bit, the mitochondria are functioning to make energy and convert it quicker, there's going to be a level of oxidative damage that's going to occur. UV radiation of the skin. Remember, I think in this video series I talked about this. My other, I know I discussed it a lot. That electromagnetic absorption into biologic tissues is going to excite electrons. Non-ionizing radiation is going to excite the electrons just to a higher level. Ionizing radiation has enough energy that when it absorbs into that electron, it bumps it free. So oxidative stress is the result of electrons kind of going haywire. So I'm going to explain more. So UV light on the skin is going to cause oxidative stress, skin cancer, obviously. Pollution, petrochemicals, all the things I talked about in my last video, all these man-made chemicals, they're not natural. They're interacting with biologic molecules and they're causing electrons to do the things they shouldn't. They're having interactions which are unnatural, of course. So heavy metals too. Heavy metals are being exposed to us at greater numbers just because we're processing things. We're unleashing these things into our water supply. Burning coal is going to put mercury into the water supply. These electric batteries that they're pushing out nowadays are just nightmare waiting to happen with all that lithium that's going to get into the water and all the other heavy metals in the process. So manufacturing of chemicals, the whole industry of all the junk we make, it's putting tons of heavy metals into our system. Drugs, recreational and prescription. I don't have to say more. When I talked about petrochemicals, that's obviously what's occurring with prescription medication. Recreational drug use, many of them are petrochemicals, some of them like cannabis, not so much on that list of being an oxidant, causing oxidative stress, but abuse of anything is going to have tax the system. Electromagnetic pollution. This is something people don't think about. This is something that's unaccounted for in almost all these conventional models. When they're talking about cancer from oxidative stress, they're not even considering electromagnetic pollution. What I mean by that is all the EMFs, the radio frequency, cell phones, Bluetooth, now we've got Starlink satellites, all these different frequencies of energy are interacting with our system. They're throwing systems off, and we're going to discuss the mitochondria in great detail, but mitochondria is not the only place that electromagnetic pollution is affecting. It's just the one that's, how should I say, resulting in radio frequency symptoms where people get sick when they first get exposed to it. So the causes, what they lead to. So what is it? What is oxidative stress? Oxidative stress is due to production of too many free radicals. What are free radicals? They're oxidants, meaning they have an extra electron. Or on the turn side of it, they can pull another electron. So free radicals, I kind of use the example when I give my talks that a free radical such as reactive oxygen species, it has that extra electron. I say it's like it's holding a hot potato and it wants to get rid of that electron. Well, in that case, yes, it is holding that extra electron and it can get rid of it. But it could also interact with something else that's missing an electron because reactive oxygen species could take on another electron. So Yeah, I'm not going to get too complicated in chemistry. I was going to start talking about that more, but we'll leave it at that. So a stable oxygen molecule is two oxygen molecules, and what's happening is the electrons within that outer shell are in a stable format. It can accept more electrons, but it cares not to unless something induces it to happen. And we'll talk about it in the mitochondria here in a minute, but things can force an extra electron onto that oxygen. So when that extra electron gets onto that oxygen, now we got this unstable form of oxygen. We got this extra electron. So it can either take in another electron and make itself stable, or it could give that electron away, which giving it away is more of what's the situation that's going to happen. We can also create a reactive oxygen species with two extra electrons. So when you look at this, it looks like it's perfectly stable. Like I was saying a minute ago, it can take that electron. Well, if it did, it would only be a temporary situation. That is an unstable structure. Those electrons are free to get off. The reason for that, which you're not seeing here in the middle, is there's a shared bond here. That shared bond makes that oxygen molecule stabilized as long as there's not other electrons there to destabilize this bond. So in simplicity, free radicals are going to donate an electron. When they donate an electron to something, it becomes a reductant, meaning that the molecule accepting an electron gets reduced. So if we have a normal biologic molecule sitting here that has different things bound to it, so I'm just putting random things here, X, C, and R. Those could be anything. It could be a hemoglobin molecule. It could be a vitamin of some sort that's bound to this protein. That electron can interact with these bonds. When it interacts with those bonds, it's going to take its place, and those things are going to pop off. Well, now we got a situation here where that normal biologic functioning protein is now an abnormal protein. The same thing can occur in the DNA. Same thing can occur to lipids. So those reactive oxygen species are going to interact with different molecules, changing their structure, leading to all the different things we're talking about here. When you've got a lot of reactive oxygen species disrupting structures, the immune system is going to start responding. We're going to have inflammation. So I'm going to erase what I have here, and I'm going to come back. We're going to talk a little more about the mitochondria. That is the main producer of reactive oxygen species. Okay, within a structure in every cell of our body, cells have between 10 to 60,000 mitochondria per cell, depending on the energy demand of that cell. So what the mitochondria is going to do is produce the energy for the cell in the form of ATP. And there's a process that the cell goes through. Anywhere within the cell, this process can occur. You can take in sugar, you can take in fatty acids, and you can take in amino acids into anywhere within the cytoplasm of the cell. Glycolysis is the first part. If you've got glucose, you're going to break glucose down to 2 pyruvates. That enzymatic process is only going to make 2 ATP, not very many ATP in the process. This is going to make a total of 36 by the end. Those pyruvates then go through this cycle called the Krebs cycle. That Krebs cycle is basically breaking that 6-ring carbon, and this is 2 3 carbon structures. So we start with 6 carbon structure in glucose. It gets broken down into 2 3 carbon structures. Within the Krebs cycle, it's going to be broken down completely into carbon dioxide. In this process of glycolysis and Krebs, we're producing molecules called FADH and NADH. Those molecules are just transporters of an electron. So while this process is going through, we're extracting electrons from that glucose. I skipped this part, I'm sorry. Where the pyruvates enter this Krebs cycle, that's where fatty acids and amino acids can also go through this cycle to produce an electron carrier. That electron carrier is going to go to a part of the mitochondria. The mitochondria is actually made up of 2 membranes. So there's an outer membrane and inner membrane, and there's a space in there. So in my drawing here, this will be the space. So we can pretend that's the outer membrane, that's the inner membrane. So these molecules are going to come up to a group of proteins. They're going to donate those electrons to that protein complex. Those electrons are going to be accepted by these things called cytochromes. So these electrons are literally going to bounce through this chain. And at the very end, they're going to get donated to oxygen to make water. As they're bouncing, they're pumping protons. So basically what's happening is we're creating a positive to a negative gradient. So the inside of the mitochondria here will be more negative compared to this space. At the very end, those protons go through the final protein, which is actually a biologic wheel. That wheel spins. As those things go through, that spinning of mechanical energy converts to chemical energy, and it makes ADP turn into ATP. So we're storing that charge separation that I talked about earlier, so that electron's creating a charge separation to create a stored charge separation here. This is the conventional model. This is what everybody's taught in school. There's a big problem. This model is highly flawed. Flaw number one, they've never proven that that gradient is very significant. There's not that much of a separation of charge. Where does all this water go? So 98% of the oxygen we consume is utilized in our mitochondria. That's a whole heck of a lot of water. The enzyme that converts ADP to ATP has never been discovered. 3 times they thought they discovered it, and then they found out it wasn't right. So they're using an energy transfer, mechanical to chemical. That's a topic that drives me crazy. I dealt with it when I was in acupuncture training, talking about chi energy. What's chi? What energy? Oh, it's energy. All these different alternative medical practices and techniques. Oh, energy. It's energy. There's frequencies. What frequencies? What energy? It's kind of one of those, when I hear the term energy, I don't like to hear it unless we're describing exactly what it is. Is it thermal? Is it electromagnetic? What is this energy? Stored chemical energy is what we're getting at the end here. So how did we get that? When I was doing my research early on, I found the flaws of this model. The major flaw of this model is when these electrons are bumping through, if they don't get controllably turned into water by that final cytochrome, and if these electrons escape, they create reactive oxygen species, those free radicals I was just talking about. So electron escape would be an inefficiency of the system. So if this system isn't pumping those protons like it should, electrons are getting out before they finalize their whole pathway of creating that charge separation, they become ROS. So as ROS increases, you would assume ATP production would decrease. That's not the case. In red light therapy studies, 60,000 peer-reviewed journals, they're finding that shining red light on a mitochondria will increase the ATP production. It will also increase the ROS. Doesn't make a lot of sense. If you expose a cell, a mitochondria, to radio frequencies will decrease the ATP and increase the ROS. So you got ROS increasing in both situations. Doesn't really make a lot of sense. So I spent about 3 months on this topic trying to figure out how is red light therapy accomplishing the increased ATP and increased ROS. It doesn't make any sense. I ran across a theory from an enzymologist out of India. His theory he's coined the Merburn process. He was running into his research where he was finding reactive oxygen species levels weren't making sense. They weren't showing to be an inefficiency of a process he was studying. They were actually showing to drive the process, meaning reactive oxygen species increase seemed to make the process that he was studying go along further. Other research, they keep on talking about red light therapy increasing ROS and how that increases genetic expression. That doesn't seem to fly very well either. How does a bad thing, an inefficiency, cause the cell to start producing more proteins? It doesn't jive. This Merburn concept, what he's saying is those electrons that get donated to those cytochromes, they're getting donated to those cytochromes because those cytochromes are actually heme molecules. Just like hemoglobin, the very center of a cytochrome has that heme structure. It's going to bind oxygen. That cytochrome is going to donate that electron that it accepted from NADH or FADH, to that oxygen molecule, creating that reactive oxygen species. This is an advantageous thing he discovered. What his theory is around that protein, you have your cytochromes, and around those cytochromes, there's binding sites for that ADP. So adenosine diphosphate binding sites are found all around those cytochromes, meaning that ADP is sitting there by that cytochrome, so it's going to be exposed to those reactive oxygen species as they're produced. So is the extra phosphates. They're just going to be within the fluid, within the matrix of the mitochondria. So those reactive oxygen species are actually transferring that electron and making the reaction, creating ATP. Pretty interesting theory. He says that there's a zone, he calls it a MER zone, around these proteins. And there's a certain concentration of that reactive oxygen species. And when the concentration of reactive oxygen species is meeting the ADP that's sitting there, there's a equilibrium of reaction. Those reactive oxygen species get used up and the ATP is produced. Well, our mitochondria has lots of different enzymes. Superoxide dismutase is the main one, where they're there to absorb these extra reactive oxygen species if the process isn't perfect. So we have a buffering system to accommodate any imbalance of that equilibrium. So oxidative stress would be caused when that concentration of reactive oxygen species is not matching up the need for ATP, meaning there's not enough of the ADP to eat up that reactive oxygen species. Or if this level of reactive oxygen species being produced within this zone is too low. If it's not at the equilibrium to produce the ATP, it's also going to cause reactive oxygen species to escape. So when that level exceeds your capacity of your enzymes to absorb it, that reactive oxygen species starts to spread in the mitochondria and through the cell. Reactive oxygen species can turn into other free radicals. Hydrogen peroxide is a big one. Hydrogen peroxide is, how should I say, stable enough it can transport through membranes. So it could be a free radical like reactive oxygen species that's ready to give off an electron when it shouldn't, but it's able to cross into the DNA, into the nucleus. It's able to leave the cell. So these things can be quite dangerous. And as I mentioned earlier, all the different processes of biologic breakdown have been linked to this. So this is why it's important. You read studies, anti-cancer effects of antioxidants. Getting antioxidants in your diet is going to be huge for your health to prevent this oxidative stress. Avoiding all the things I had in the other column there, except sunlight, and just avoid excessive UV exposure sunlight in the middle of the day. But you don't want all these drugs. You don't want all these petrochemicals in your body. You want good things that are going to help neutralize oxidative stress. So where does red light therapy come in? Red light therapy is absorbed into those cytochromes. Those cytochromes are pigments. They absorb electromagnetic energy. That frequency of red is the frequency that's optimal for this mitochondria or for this cytochrome to create this reaction, to create the reactive oxygen species. So frequencies of red light are important, and it's tuned, meaning these cytochromes absorb a very specific wavelength in that frequency. Remember when I was talking about semiconductor nature of the microtubule system? Those microtubules are going to put out a very specific frequency that's going to make this reaction occur. For all we know, the quantum system could be so complex that it makes different frequencies for different needs of the ATP. So when the cell's very active, it's going to put out a different frequency to bump out those reactive oxygen species faster. The complexity of the biophotonic system, and we know nothing about it because they're not studying any of this. They're stuck in their chemical reactions. They're still looking at these processes, and they're creating agents that block that process or skip a step and facilitate another step that happens more rapidly than it should. So we're kind of in that mess with conventional medicine where we're still thinking these ways. When I talked about this, conventional medicine with their model that they had that completely is wrong, it's flawed, and one of the themes in conventional medicine is irreducible complexity. All we were trying to do was create a charge separation. We were trying to create an electron charge separation to create a reaction, okay? What did biology do? They made this highly complex step with multiple reactions, and all it was trying to do was create a charge separation. Now, what did that charge separation is eventually going to store in ATP. They had to come up with a theory of a rotary wheel and mechanical energy, chemical. When you look into it, you kind of sit there and go, we basically needed to take ATP, store a charge separation in it, and we just needed to create a charge separation. What they missed was that electromagnetic energy is the driving force that creates that charge separation. They never really, no, I won't even go too far on it. It doesn't make a lot of sense. So when I talked about radio frequencies causing people to be ill, this location of the mitochondria is where the illness is coming from. Radio frequency illnesses, I'm going to discuss in another video, is the result of not making ATP and producing too much of this reactive oxygen species that diffuse. When that occurs, the body gets weak. So fatigue, body aches, mental disorientation. When reactive oxygen species levels are out of balance, the mitochondria is creating more heat, fever. So all the symptoms that we attribute to influenza, being sick, most of what we're dealing with when we're sick is not an infectious disease, but a state of mitochondrial dysfunction. And it will make more sense as we get further along. But this being out of balance is important because that's the main way our cells produce energy. And if this isn't occurring, cells don't function. They get sick. They can't function. So next video, I'm going to be discussing how our body uses ATP, how our cells are using ATP. So I hope that this made sense and I presented it simple enough. And I'm sure I'll be back on it again at some point talking about it. So thank you. I hope you enjoyed the video.